Howdy, everybody. Hope you're doing well wherever, whenever you are. We're here for more Advent of Code, solving some problems. So far, this year hasn't been too tough. That may change. I have no idea. But if you're following along, I'd love to see your solutions. Love to see your comments. Um, it's always fun to like compare and contrast solutions. So I'd love to see what you're doing. Anyway, with that, let's just start. We're now on day 16. So it is Aunt Sue. Your Aunt Sue has given you a wonderful gift, and you'd like to send her a thank you card. However, there's a small problem. She signed it from Aunt Sue. Okay. Oh, you have 500 aunts named Sue. Okay. So to avoid sending the card to the I sorry, I paused for a second there and I'm like, how's that even possible? But we'll just go with it. So to avoid sending the card to the wrong person, you need to figure out which Aunt Sue, which you conveniently number 1 to 100 for sanity, gave you the gift. You open the present, and as luck would have it, good old Aunt Sue got you a My First Crime Scene Analysis machine. Just what you wanted or needed, as the case may be. The My First Crime Scene Analysis machine, MFC SAM for short. I don't know if I want to say that because I this part of it, it's not great. Can detect a few specific compounds in a given sample, as well as how many distinct kinds of those compounds there are. According to the instructions, these are what the MFCSAM can detect: children by human DNA age analysis, cats, it doesn't differentiate individual breeds, several seemingly random breeds of dogs, Samoyeds, Pomeranians, Akitas, and Vislas. I've never seen these two before. Goldfish, no other kind of fish. Trees, all in one group. Cars, presumably by exhaust or gasoline or something. Perfumes, which is handy since many of your Aunt Sues wear a few kinds. In fact, many of your Aunt Sues have many of these. You put wrapping you put the wrapping from the gift in to the machine. It beeps inquisitively at you a few times and then prints out a message on the ticker tape. That's funny. It provides a link. Maybe people haven't seen ticker tapes before. We probably don't use them in the modern day. Children 3, cats 7, Samoyeds 2, Pomeranians 3, Akitas and Vislas zeros. Goldfish 5, trees 3, cars 2, perfumes 1. You make a list of things you can remember about each Aunt Sue. Things missing from your list aren't 0. You simply don't remember the values. What is the number of the Sue that got you the gift? To begin, get your puzzle input. Okay, so we're given a bunch of Sues and what we remember. So like Sue 499 has 6 perfumes, 3 goldfish, and 7 Vislas, or whatever that is. In fact, many of your Aunt Sues that we put them. Things missing from your list aren't 0. You simply don't remember the value. Okay, so it's like a matching problem. I mean, I think that's right. I think we just go through the list and check. So like what I'm thinking is like this Sue right here, 395. We know she has 4 Vislas. But this one says 0, so it clearly can't be her. The idea being we can immediately eliminate anyone who doesn't have any of these. And I think we're just checking, and then we're checking for exact values. but only if uh, they're in the list that you remember, right? So I don't like this one doesn't have Wislas. We don't know that it's 0 though. We just don't know that this is it. So I think we need to check to make sure it's not 0, or we should check to see if it's in this list, and then if it is, make sure it matches the values we expect. Okay. Uh, hopefully that didn't cause any problems. So I think the next step is to or to the next step. The first step is to do parsing. Okay, so we got the stuff here. So let's just write, what do we want to return for each Sioux? We could create a data structure. It's mostly empty. I'm only interested in searching for like these specific values though. So I'm inclined to just return like tuples, an array of tuples that says children this, cars this, Wislas this. It looks like all of them are threes, but we could do some splitting and parsing to get those tuples, right? Because the only ones we actually want to check are these. So, like for Sioux 1, we'll say, oh, it's children 1, our cars 8, our Wislas 7. I'm sure I'm saying that wrong. I apologize. Should I just go look it up and see if it's got Samoyeds? 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 Wislas? Wisla? Okay. Oh, and we know that. So this is what we're looking for. Yeah. So let's write a parser for each line. Um. We'll want to return like the ID, I guess, and a vec of tuples, which will be a stir and I guess I size. I'm gonna have to use a lifetime here for these. I could just cast them as strings, but oh. Hmm. I think they're all in threes. Each of them only have 3. So there's a potential to say, oh, I just get this value, 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 and like trim off these. I'm more inclined though to split by comma. So like if I do I may actually want to use nom here. Let's just do some string parsing. Like I was thinking in nom we could say let's create a tuple for this, and then we know there'll be n number of those, and then expect Sue, and then some number. So we'll say let parts equal line dot split. Is there like a split n? Yeah, split n. 1. Like that. And then we do, oh, I'm missing one of these. Like let what are these things called? Compounds equal parts 1 dot split by comma dot collect. And then actually we can also, I think we can do it at one time. Because we can do split by commas, then we do a map of the part. And so let parts equals split p dot split and then we just return parts dot next. Oops. Like that. Right? So it's going to split by the semicolon in the space, and I just return like each of like this one, and then this one as an integer. Oh, so I need the ID here. I mean, so because it's an order, I actually don't know if the ID is that important. So let's just not parse it. I mean, it's not hard to parse it from here, right? You just say, give me the second or whatever. In fact, we can just go like this and trim. Oh, we gotta unwrap it. Dot trim. Start matches for Sue. Dot parse. Dot unwrap. Like that. That. Oh, I don't need to parse this. Oh, yeah, I do. Oh, I'm not parsing it. I'm just returning the string value of it, which is probably okay. Right? So this is going to return a string version of 1, but that's fine. So let Suze equals input.lines.map parse.collect. Like that. Let's just look and see if we get them. This unwrap doesn't like. So parts next unwrap. Which one are we on? Is it like literally the first one? I'm probably overcomplicating the parse here. So we can look to refine it. Maybe we'll use num later. So we have line.splitn. Return an iterator over a substring given separated by a pattern. Restrict returning at most. Oh, I have 1. That's it would never return more than 1, right? Okay, let's just check that. Ooh, we got spaces. So we'll fix that. But cars 1, perfume 6, Vislas 1. So we have spaces in the name, which is this one. Okay. Now I think okay, so now I mean, I think we can just hard code this value, these values right here, right? So we can say so we split the line. We split the line is what I'm thinking by like like that. And we just return parts.next.unwrap and parts.next.unwrap.parse. A hash map over stir and iSize. Okay, so now we have the expected list and we have the SUs. And now we just want to check for each of the SUs if these values are exactly equal to what's in the expected. So it'd be something like for compound in compounds, if expected dot get compound 0 dot unwrap equals I guess we can just return name dot. Oh, I do return it as an I32, so we'll make it an iSize. So I will make this one a iSize. Like that. I have to dereference this, I think. This. Okay, like if it fails, we return 0. So, but what like essentially what am I trying to do here? We're parsing the lines, so now we get all of these as well as the number, I guess. And then we're going to compare it against this expected, right? We turn the expected into a hash map. And then we go through the list and we say, "Hey, go get the compound and make sure it's equal." But we only do it for the ones here, right? And if we ever find that one that's equal, we found it. 5% sure. 4. So why would 4 work? Goldfish 5. Children 8. That does not work. I'm doing it the wrong way here. If they're not equal, we want to continue outer. And then if we get here, we return name. Like that. 213. So we can spot check this before we solve it. 3 children. Yeah. 5 goldfish. 0 Wislas. So that one does work. Okay. Not too shabby. So again, it's just a matching problem, right? We're saying, here's a list of what it spit out. Can we find one of these that meet our criteria? And so we parse the expected, We parse the SUs. We go through each of the SUs and find the thing. We could even simplify this right here, right? We could say like input dot lines dot map parse like that. Okay. Let's move on to part 2. As you're about to send the thank you note, something in the MFC SAM's instructions catches your eye. Apparently, it is an outdated retro encabulator. Okay, we're going to go down a hole. Oh, okay. This is an older video. Yeah. This is like he's like I won't play the video, but he like says a bunch of things that aren't real things. So anyway, it's kind of funny. And so the output from the machine is an exact value. Some of them indicate ranges. In particular, the cats and trees reading indicates that there are greater than that many due to the unpredictable nuclear decay of cat dander and tree pollen. Okay. While the Pomeranians and goldfish readings indicate that there are fewer than that many due to modal interactions of magnetor reluctance. What is the number of the real Antsu? Okay, so this is part 1, but now we just need to check for cats, trees, Pomeranians, and goldfish. And they need to be greater than for cats and trees and less than for Pomeranian goldfish. So the problem doesn't actually change in like this structure right here. It's just determining this part right here. Right here. Can I do like a match statement? So I do like a match compound dot zero. Oops. And I'll say if it is cats or trees, then I want to do something so kind of like this. And then what's the other one? Pomeranians and goldfish. So we'll get the count and we'll say this one has readings indicate that are greater than that many. So we say if this is like the true case. Oh, so I guess I can do the opposite way. So I say if it's less than or equal to the count. that. And then I say if compound dot one greater than or equal to count, continue outer. Otherwise, I just do the normal. So if I say if like that. I think that's right. Let me just read it through for 1 second. So I'm still going through the list. I'm going to get the count of the expected, and I'm going to match on the compound. And if it's cats or trees, I'm going to say if that compound is less than or equal than the count, I want to skip it. If it's Pomeranians or goldfish and it's greater than equal, I want to skip it. Otherwise, I just check if they're not equal and skip it. I think that's right. But we can probably simplify this. But let's just try it, see what we get. 323. That's the right answer. Okay. Not too bad. Again, it was just a matching problem. So, and part 2 just added some extra checks. So, I think maybe what we do now is look at how we can refine it. But again, I don't think it was that big of a deal. Maybe depending on how you did this would change how you set it up. My parsing looks kind of ugly, so maybe I'll try and fix that. I want to kind of hone in first on this, because I think you can do like is it and or is it like where? I actually don't remember this syntax. Is this thing going to work today? In a match statement, how can I add a conditional? Not looking good. Oh, if, not where. So like that. Uh, like that. Okay, so you can do matches like this. It's not clear to me. I mean, it's definitely less code, but it's not clear that this is necessarily more readable. I mean, I don't know. It feels more readable. Is it the same though? 213, 322. Yeah. Oh, what did I do? Did I miss something? For or, the guard applies the whole alternative. Binding names must be compatible across alternatives. The guard sees variables. If the guard evaluates defaults, the match continues. If the guard calls, if the guards can. Oh, here's why it's failing. So why doesn't this work? Is because down here it then checks equality. I think. So you'd have to do something like that, I think. Yeah. So like what was happening is like if a cat or tree was greater than, it would then come here and check the outer. It it would come down here and say, "Oh, they're not equal." So now I need to blow up. So this is where those conditionals sometimes don't make sense. Um yeah, I'm not a fan of it, so it's possible that I may want to just like switch it up. Go back to something. If you have another way to show this, that would be interesting. Like instead of the if logic, you could just do another match. Like you could say like this. I think that solves it the same way. Yeah. That probably makes more sense. Sometimes these nested matches make more sense than the ifs. It's probably a matter of preference, but I this feels like it looks better. Uh I could also use the matches statement. I could also do like We could ask GPT-5 what it says. Is there a way to make this match statement more concise or more readable? Do you think about what I have? I'm inclined to say like this is pretty good. You could add if blocks here as well. Nested matches are okay. Um there's also like the matches, the bang matches. So you could say like if bang matches, you know, or matches bang, cats trees count, or dot dot dot, or dot 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 continue. I don't know if that's better though. We'll see what the AI says. I think for now this is, well, I don't. I'll replace the nested Boolean matches with a concise helper closure and destructure. Oh, this is an interesting idea. So like what it's doing is it's kind of saying, uh if you give me the key and the size and the count, I'll do a test. And so if it's this, it should be less than or equal to. If it's this, it should be greater than or equal to. Otherwise, it should be not equal. And then it can just go through each of the compounds and determine if it's a mismatch. This is interesting because now we could apply a um, like a functional all to it or something like that. Let's keep this. First of all, let's make sure it works. And because this has an interesting thing is that we could use it to solve part one as well. Yeah. So what could we do here is we could say, if compounds dot all or iter all return not is mismatch. Like that. Now we don't even need the iter. I think that does the same thing. It does not. Oh, I think it's because I want to return the opposite of it. The mismatch is like weirdly named. No? Really? There's something wrong in the law. So for each of the compounds, I want to iterate over them, and all of them, just make sure, test if every element of the iterator matches a predicate. And my predicate is not is mismatch. So for cats or trees, how would I change this to a match? Is match. So for cats, it's probably should be greater, less. Equal. So all should be a match. There's no way that's the case. Children 1. Name count expected. So match name, cats or trees, the count should be greater than the expected. For Pomeranians and goldfish, the count should be less than the expected. Otherwise, the count should equal the expected. I'm dumb. Okay, there you go. I think moving it to is match either as well makes more sense. But now I could do this. I could do this all in like one batch. Right? You could say input dot lines dot map parse dot is it find? Yeah. So we want to do a find on name compound where this eye size is not an iterator. Hmm. Oh, it's like this, right? I just do this. Yeah, I'm not using that name, so I guess that makes sense because the name. Okay, so does it make? I've made this super functional, and I don't know if it makes it better or worse, but the idea is go through all the lines, parse it, do a find. So find is going to find the first one, and the condition is where compounds iter all is a match. And then I just unwrap and return the first one. Again, there's not a lot of error handling here, but this works. So I can actually do like now I can do this for both of them. I want to pass this as a function. I'm doing this wrong. I know I am. That. I'm not remembering exactly. Okay, it's like this. Oh, I was doing it the wrong way anyway. I have those in the wrong order, huh? That. I think that's right. It's not giving me any errors anymore, and I got the right answer. Okay, so I basically just create a closure, and then I pass it to this fn match. That we're going in the woods here trying to solve this in a funky way. But I'm basically using higher order functions, right? So you give me a function that says here's the match, and then I'll return the way to do it. And like what that means is now I can do this in part one. And part one is like this function is literally just count equals expected. I think that'll do it. Yeah. There you go. Okay, so the parts now are like essentially the same. You give it a match, you create a match function. For part one, it's just we're literally checking equality. For part two, we are checking equality, but we have the special cases of cats or trees need to be greater, and Pomeranians and goldfish need to be less. And then we just call this find match. And what does it do? It parses the expected list, goes through each of the lines of the input, parses them, and then for each of the compounds, checks to make sure that that match applies to all of them. And if it does, then we've solved it. So there you go. It took a little bit of rewriting. Do I want to rewrite this? I feel like we've been going for a while, so I'm sort of feeling like maybe we just leave it how it is. One of the reasons I like using nom is because you don't get these, parts, next, unwrap, parse, unwrap, next, unwrap, parse, unwrap, next, unwrap, parse, unwrap. It kind of abstracts that away into an error that you can just like unwrap once when you're doing these puzzles. But I think I'll call that good. We'll stop here for this one. So maybe you have a better parsing function, or if you did it in nom, send it my way, and maybe I'll update mine and show you showcase your changes to the small world that's watching these videos. But there you go. Day 16 is in the bag. Again, it wasn't too hard. A lot of these days so far have felt like if you probably taken like one computer science class, you could probably solve them. Although some of them do require you to do permutations, and maybe if you don't know how to like iterate through all the permutations, that may be a little hard. But I don't think we've used any like crazy algorithms so far. We'll see if that changes though. Talk to you next time.